Hey guys, hang on a second. Hey guys, where was I going with this? Oh, okay, yeah. So we're gonna do another flipped classroom thingamajingy. We're gonna talk today about limiting reactants and all types of yield, theoretical and otherwise. Let's see, and then of course we'll just do more. We'll do more practice problems in the class, so it'll be super great. High quality content. Let's jump into this right out of the gate. But first, don't forget to hit that like, share, subscribe button, and be sure to ring the bell for any notifications to get more information on chemistry videos that we are sharing amongst ourselves. All right, let's see. It always takes me like 10 million years to find the share screen on here, which makes no sense. But oh well. Oh wellsers. Okay, let's jump into this. I have often dreamed of a far off place, a great warm welcome. All right. Okay. Let's make sure we have enough space here. That's a goodly amount of space. Let's make sure we have the appropriately sized pen. Yes, the calligraphy brush at 2x. Ooh. Nandayo. Let's zoom back a little bit. There we go. Okay, that works. Alrighty, let's jump into this then. Okay, so as I mentioned today, what we're gonna talk about something called limiting reactants or limiting reagents, and then we're gonna talk a little bit about theoretical yields and percent yields and actual yields. So we'll do limiting reactants over here, limit reactant, and then we'll push the theoretical yields over here. Let's do yields. Alrighty then. Okay, let's see. So each of these relates to this concept of moles that we've been talking about. So it relies on our ability to convert between grams and moles and things like this. So as always, you definitely need to have these equations on lock. The grams, the conversion to grams, excuse me, and then the conversion to moles. Okay. Have those guys burned into your noggin. What we're going to talk about here is the concept of stoichiometry, which is relating one type of molecule in the chemical equation to a different type of molecule in the chemical equation. So let's unpack that a little bit. So let's say that we have a standard chemical equation like CH4 reacts with O2 to form H2O and CO2. Let's balance this real quick. That's good. That's good. Okay. Okay. Now, let's say that you're doing this reaction one day, and you're like, oh, okay. Let's say I picked up 15 grams from the store of methane, and I picked up, let's say 20 grams of oxygen from the store. And so then you ask yourself, well, G self, which one of these things is going to run out first? Which one of these things is going to run out first? That is a question that involves the concept of the limiting reactant. So limiting reactant. Actually, you know what? I'll just do a little text box because it's so much easier to type. So limiting reactant can be described as the reactant that is completely consumed in the reaction. Okay. That reactant that is used up first. That's our limiting reactant. Now, just from an intuition perspective, you may be like, well, okay, Dr. K, there's 20 grams of oxygen and there's 15 grams of methane. So intuitively, you'd say like, well, there's more grams of this, right, than there are grams of methane. So that means that the methane should run out first, right? That makes sense intuitively, but it doesn't make sense when we start to look at an actual how chemical reactions work in reality. Okay. So again, if we were to zoom in on this chemical reaction, every single time, that we would do this reaction, we would use one molecule of methane and we would use two molecules of oxygen. Okay. So that means that we're using up oxygen at a faster rate, right, than we're using up methane. Okay. So that's one thing that can already adjust it right out of the gate, right? If I'm using up one molecule faster than the other, even if I have a greater starting amount of oxygen, that doesn't necessarily mean that it's going to last longer, because the rate of use is going to be different, or sometimes is different, right, when we're doing a chemical reaction. So that's the first thing. The rate of use changes. The other component that's worth noting here is the molecular mass. Okay. Now, each one of these molecules, right, can also be used to represent the coefficients, can also be used to represent moles as well. Okay. Because remember, a mole, all that a mole is 6.02 times 10 to the 23rd things. Okay. So if I'm doing this chemical reaction, I can either use one molecule of methane with two molecules of oxygen, or I could use 1 mole of methane molecules with 2 moles of methane molecules, right? It's kind of like saying 1 pair of molecules would go with 2 pairs of oxygen molecules, or 1 dozen methane molecules would go with 2 dozen methane molecules. Similarly, 1 mole of methane molecules would go with 2 moles of oxygen molecules. Okay. Now, what that means then, since not every single atom or molecule weighs the same, right? That means that 20 grams doesn't even necessarily mean that there's more molecules, even though it's a higher mass. Okay. I'm going to say that again. Just because there's a higher mass of oxygen than there is of methane, that doesn't mean that there's more molecules of oxygen than there are molecules of methane. Let me give you a simple example over here. Let's say that I have 10 grams of hydrogen. Okay. And then let's say that I have, let's say 24 grams of magnesium. Okay. Magnesium's molecular mass is approximately 24. Okay. Now, there's a much larger mass right here, over twice as much in terms of the mass of magnesium. But if I converted these guys into moles, right? So the mass, if I want to go from grams to moles, then I always do 10 grams divided by the molecular mass of hydrogen, which is 1. So that means I have 10 moles of hydrogen. Okay. Magnesium, again, broad strokes, its molecular mass is 24. So 24 divided by 24 would mean I only have 1 mole of magnesium. That means that I have 10 times 6 times CO2 times 10 to the 23rd molecules of hydrogen. So I have 10 times avocado's number of hydrogen atoms, and I only have 1 times avocado's number of magnesium atoms. Okay. So even though I have a much bigger mass in magnesium, because individual magnesium atom weighs so much more than an individual atom of hydrogen, right? That means that we still have way more moles of hydrogen than I have moles of magnesium. And therefore, I have more atoms of hydrogen than I have more atoms of magnesium. Okay. So to put this all together, this first bit, there's two things that influence what's going to be the limiting reactant. Number one is the amount of molecules present, right? And again, just because something has a bigger mass does not mean that it's going to have a greater number of molecules present. So number one, the amount of molecules present. And number two, how rapidly those things are being used up. Okay, that's what dictates the limiting reactant. Now, how would we go about solving for a limiting reactant? And there's a couple of steps that we were going to do. And then I'll walk through this with this example, okay? So how to solve for limiting reactant. Number one, convert grams of each reactant to moles, okay? And you do this using the moles equals grams divided by molecular mass, okay? First step, convert grams of each reactant to moles using our equation. Okay, so in this case, actually, we'll walk through this in a second. So the first step, convert grams of each reactant to moles using molecular mass. If you already are given moles, sweet, then you don't even have to convert grams to moles. But normally you're going to be given grams and you'll be like, hey, which one is the limiting reactant? So the first step, convert grams to moles. Once you figure out how many moles of each of the reactants there are, then you're going to divide each set of moles by the corresponding coefficient on the chemical equation. What does that mean? That means then that when I figure out the amount of moles of CH4, I'm going to take that number of moles of CH4 and divide it by the coefficient of CH4. Okay, the coefficient for CH4 is 1. Similarly, when I figure out how many moles of oxygen there are, I'm going to take the moles of oxygen and divide it by the corresponding coefficient of oxygen, which is in this case 2. So this tells you how many times your reactant, each reactant, I guess, can power the chemical equation. Okay. So the larger the number then at the end of this step, right, that means it's going to be able to power more cycles of the chemical equation. It doesn't mean that it will, but it has the capacity to do that. Okay. The lower of these two numbers, or of these numbers, I guess, if there's more than two reactants, the lower of these numbers is the limiting reactant. Why? Because the lower the number, right, that means that the lowest number is only able to fuel the smallest amount of cycles. Okay, so let me put this into an example. Okay, so if I have actually, no, let's just walk through this problem, and then we can do it. Then we can hopefully crystallize this concept. Okay, so the first step, convert grams of each reactant to moles. Okay, so I have 15 grams of methane. Now, if you look at the periodic table, carbon is 12, and then there's 4 hydrogens. So each one of those is 1. So 12 plus 1 plus 1 plus 1 plus 1 equals 16. Okay. So I'm going to have CH4 and then O2. Okay. So CH4, the 15 grams, and then 16 AMU for the molecular mass. So 15 divided by 16 means we have 0.94 moles. Okay, so again, based off of the 15 grams that we have, we now have know that we have 0.94 moles of methane. Okay, oxygen, on the other hand, each one of these oxygens is 16 AMU. So that means that the molecular mass of this oxygen molecule is 32 overall. Okay, so I take similar equation, 20 grams, because that's the amount of grams that we have, divided by 32, and that equals 0.625 moles. Okay. So now already right out of the gate, even though we had a larger mass in terms of, so we had more grams of oxygen than we have grams of methane, but because oxygen weighs so much more than methane, we actually have fewer moles of oxygen than we have moles of methane. Okay. So first step, convert grams of each reactant to moles of each reactant. Now, the next step is we divide each set of moles by the corresponding coefficient on the chemical equation. Okay. So that means we take, for CH4, we take the 0.94 moles and we divide it by the coefficient of methane. Since there's no coefficient here, and that does not say OCH4 now, the coefficient here is 1. So our number there is 0.94. Okay. That means that this amount of methane is able to power, for lack of a better phrase, 0.94 cycles of this chemical equation. Okay. It's actually 0.94 times Avocado's number, but you don't need to worry about that. We have this number. All right. O2, on the other hand, we have 0.625 moles. And the coefficient for O2 is 2. So the coefficient at the beginning right here is 2. So if you divide that by 2, we'll end up with 0.3125. Okay. Now, the lower of these numbers is the limiting reactant. So again, because we have this amount of moles of oxygen, so fewer molecules to begin with, and we're using them at a higher rate, which is what this denominator tells us, that means that we can power fewer cycles with oxygen than we can with methane. Okay, so the lower of these two guys is the limiting reactant. Okay, so let's go through this again. In order to figure out the limiting reactant, number 1, convert grams of each reactant to moles using our moles equals grams per moles, molar mass, equation, right? Secondly, once you figure out how many moles of each of the reactants there are, divide those moles by the corresponding coefficient. So for CH4, I divide it by the coefficient of CH4. If I have O2, I divide it by the coefficient of O2. What that's going to do is that's going to tell you how many times that set amount of moles can power the chemical equation. And since the lower of those numbers, right, means that can power fewer of the chemical equation, the lower number is the limiting reactant. Okay. Notice that this is not the same thing as moles of reactant. We already calculated out what the moles of the reactant are. Okay. This just tells you how many times that particular amount of moles can run the chemical equation. Okay. Now, let's see. Sometimes there's a couple different wrinkles that will show up here. Sometimes instead of being given grams of a reactant, you're just given moles of a reactant. And if you're given moles of reactant, that's totally fine. All you got to do is start at this point instead of at this point. The number 1. Start number 2 instead of number 1 if you're just given moles. Okay. The other thing that you'll see sometimes is you'll hear this term in excess. So how I would phrase this question would be something like, let's say that you have 15 grams of CH4 and an excess of oxygen. So in excess or an excess, whatever. One reactant is described in terms of excess, right? And then but I won't give you like how many grams of oxygen there are, right? And so then you'll be like, oh my gosh, Dr. K, there's no way I can figure out what the limiting reactant is. As soon as I say in excess, I say that a reactant is in excess, the other reactant is the limiting one. Okay. So if I said, hey, I have 15 grams of methane and an excess of oxygen, then you know that methane is going to be the limiting reactant. So whichever reactant is not in excess, that's going to be our limiting reactant. Okay. Any question? Well, I guess I'll address questions in the actual lecture. But let's see. Okay. Okay. I'm going to leave that there for now, the limiting reactant stuff. I think that should cover everything. Again, a lot of this is just practice. So, limiting reactant, you just J-chill over here, my guy. And then let's move over to the yields. Okay, now, limiting reactant, that seems pretty intuitive, where it's like, okay, we're trying to figure out what is the thing that we're running out first. Another common equation, yikes, I need to go home. Another common question you can ask is, how much are we making of a thing? Okay. And that is a question about yield. So, what is the yield of a chemical equation? What is the theoretical yield? What is the actual yield? What's the percent yield, right? But essentially, they're all asking about how much of the product are we actually making? Okay. So, now what this means, let me rewrite this equation actually. Excuse me. Let me rewrite this equation over here because I think that'll be helpful. Okay. Okay. So let's say that I plugged in a certain amount of grams of methane, right? Then the yield question would be like, okay, if I've plugged in X amount of grams of methane, how many grams of CO2 am I going to get out the other side? Okay. That seems like a pretty logical question, especially for the context of chemistry. So what that means then is that I have to figure out a way that I can go from moles of one thing to moles of another thing. Okay. I have to have a conversion from moles of one thing to moles of another thing. Now, this gets into the concept of stoichiometry, which is essentially the process of converting from one type of molecule into another type of molecule using a balanced chemical equation. Okay. The coefficients on a balanced chemical equation are what's called stoichiometrically linked. All that means then is that if I wanted to convert from moles of one thing into moles of another thing, all I need to do is have the coefficients of a balanced chemical equation. I'm going to say that one more time. Lock this one in. If I want to change from moles of one thing to moles of another thing, all I need is a balanced chemical equation and the coefficients from each of those molecules. Okay. Now, how do we do this? How are we going to do this? There's a nice formula that I might have come up with on my own. I'm very, very smart. It looks a little something like this. So, how to convert from moles of X to moles of Y. And obviously, you can slot in any moles you want. Okay. So, this goes for like if I want to convert from methane to oxygen, from methane to water, from methane to CO2. All right. So, how to convert from moles of X to moles of Y. Number one, convert from grams of X to moles of X using that standard formula that we've done multiple times now. So moles equals grams divided by molecular mass. That's the first step. Again, like before, sometimes you'll just be given moles and then you can just skip that step. But usually you'll be given grams and asked to turn it into grams of another thing. Okay. So convert from grams of X to moles of X using that formula. Next, you're going to convert from moles of X to moles of Y by, where is it? Oh no. Oh, Discordia. I got to put another one. Yikes. By doing this formula. So you'll take moles of X and you're going to multiply it by the coefficient of Y divided by the coefficient of X. And what that's going to do is that's going to change it into moles of Y. Okay, so what this means then is if I want to go from moles of one thing to moles of another thing, I have to take the moles of that starting material, multiply it by the coefficient of what I want to turn it into, and then I divide that number by the coefficient of my starting material. What that's going to do is that's going to change it from moles of my starting material into moles of my ending material. We'll go through an example of this in a second, actually. And then the final step is convert from moles of Y to grams of Y. Again, using that beautiful equation that we had. I told you, you guys were going to use this all the time. And so you are. Convert from moles of Y to grams of Y using grams equals all that, whatever. Okay, so that's how we can use that for anything. If I want to change from grams of methane into grams of oxygen, if I want to change it from grams of methane to grams of water, whatever the case may be. So let's do a practice problem right here. So let's say that I had, yikes. No, please stop it. No, turn that off. Go away. Go home. Okay. Let's say that I had 20 grams of CH4. What's the number of grams of H2O that I get out of that? Okay. So grams of CH4, how many grams of H2O do I get out of it? The first thing I want to do is I'm going to convert from grams of X to moles of X, so grams of CH4 to moles of CH4, by dividing the grams by the molecular mass. So for CH4, I'll take 20 grams, divide it by, again, if you go back and take a look at the periodic table, you can infer that the mass is 16. Excuse me. So that means 1.25. Where's my, there we go. Equals 1.25 moles of CH4. Okay. So that's how many moles of CH4 I have. The next step is I need to convert from moles of X to moles of Y, moles of CH4 into moles of H2O. This is why you need to have a balanced chemical equation. If you don't have a balanced chemical equation and it's just ridiculous coefficients, then you're never going to be able to accurately convert from moles of one thing to moles of another. Okay, so 1.25 moles of CH4. In order to go to moles of H2O, I use the coefficients. So I take the moles of X, which is CH4, and I multiply by the coefficient of Y, so what I want to turn it into, in this case, divided by the coefficient of X, which is where I'm coming from. The coefficient for H2O is 2, so the top is 2. The coefficient for CH4 is 1, so the bottom is 1. And that will turn it into moles of Y. So if I multiply this out, I'll end up with 2.5 moles of H2O. Now, the last step is to convert from moles of Y to grams of Y using, again, this equation. So grams of H2O would be 2.5 moles of H2O times the mass of H2O. And if you use the periodic table to figure this out, oxygen is 16 and there's 2 hydrogens, each of which is 1, so that'd be 18. So that means overall, 2.5 times 18 equals 45. So that means at the end of this, I'll have 45 grams of H2O. Wow. Now again, this means I can convert from, as long as I have a balanced chemical equation and I know the amount of grams or moles of the starting material, I can convert from from anything to anything else using this balanced chemical equation. Okay. Really, really fundamental skill. Now, again, there's a couple different things I want to point out here. This is what's called the theoretical yield. Wait, I better scroll down because I've been realizing that my face just gets in the way of this whole thing. Let's see, make sure that I'm okay. Okay. So this is the theoretical yield. Okay. So this is the assuming that the reaction completely finishes, right? Everything gets totally used up. This is the maximum amount that you can possibly get. The theoretical yield is the maximum possible product. Maximum product. Now, just because it's the maximum product doesn't mean that you get the maximum product. Okay. Obviously, and maybe you guys have already started to pick up on this in lab, when you do science, it's pretty messy, right? And so even though you think you're doing it totally perfectly, sometimes you can just have some kind of error, right? So it's very rare indeed. If you can get the theoretical yield, then you're like some godlike scientist. But it's very rare, not impossible, to actually get to the theoretical yield. So what we usually talk about is the actual yield in conjunction with the theoretical yield. So the actual yield is the actual product. Okay. So in this case, the maximum product was 45 grams. In the actual yield, it would be something like, oh, I don't know, let's say 38 grams. Okay. Now we can put these two things together to make something called, excuse me, guys, sorry, to make something called the percent yield. Now, this is a way that we can measure how effective we were at producing our product. Okay. So what we do is we take the actual yield, I'm going to say AY here, and we divide it by the theoretical yield, TY, and then we multiply that by 100. Now that's going to give us some number that is a percentage. Okay. And that'll tell you how close we got to producing the maximum product. So in this case, right, we have 38 as our actual yield. So if I do 38, and then our theoretical yield is 45, divided by 45, and then I multiply that by 100, then I end up with 84.4. Okay. So that means my percent yield is 84.4. Okay. I took the actual yield, divided it by the theoretical yield, and multiplied it by 100. That gave me the percent yield. The closer this number gets to 100, the closer this number gets to 100, the closer your actual yield is to your theoretical yield, and the more successful you were at producing your product, typically. Now, sometimes what can happen, right, is you get a false number in this actual yield. Again, as I mentioned, science is a bit of a messy business, right? So you can have your product, but maybe it has a contaminant in it, right? And so now where you think the maximum you should get is 45 because you have a contaminant in it, well, now the mass is like 100 grams or something like that, which is way past the theoretical yield, right? In those cases, right, usually it's due to some kind of contaminant. Oftentimes what will happen is folks will not fully dehydrate and remove all of the water from their sample. And so when they have their sample, not only do they have their product, but they also have a whole bunch of water in there, which weighs the whole thing down. And so your actual yield mass is way, way, way bigger than your actual theoretical yield. So your theoretical yield, not your actual theoretical yield, right? So that's another thing to keep in mind. Sometimes you can have false positives with your percent yield. But those are the three types of yield. Theoretical yield, which is the maximum possible amount of product that you can get, which you learn from stoichiometry, which is what we did up here. There's the actual yield, which is the amount that you are actually measuring in lab, right? The actual amount of product you had at the end. And then there's the percent yield, which is the how close those two things are together. And you take that by doing the actual yield divided by the theoretical yield and dividing by 100. Okay. Now, I'm not going to do a practice problem for what I'm about to say, but this is something I want you guys to be aware of because oftentimes these two things will be pieced together. What I'll do is you can say, hey, let's say that I had 20 grams of methane and then 20 grams of oxygen. And then I would ask, number one, what is the limiting reactant? And then number two, what is the theoretical yield? That's another question. Like you could blend those two questions together. Now, all you have to do is put these two things together and then you've solved it. The first step, solve for the limiting reactant, right? Once you've figured out the limiting reactant, then you can use that to determine what the theoretical yield is. In fact, let me check how long this is. Maybe I might have time. Yeah, I'll do it really quick just for our own edification. Because I feel like this can be, I'll show you like a difficult problem that you can ask from this. Okay. Let's say I have, oh, I don't know. I'm trying to think of a good reaction. Let's do HCl plus NaOH reacts to form H2O. I really want something that like has different coefficients. All right, let's just do this one. This is a good one, I guess. Gross. Aluminum plus O2 reacts to form aluminum to oxygen. So this one's going to take 2. I'm going to do 3. This is going to be 4. Okay. All right. So there's our chemical equation. Now let's say I'm going to break out my own periodic table for this. Hang on one second, guys. I don't have aluminum memorized off the top of my head. Okay, so let's say then that I have, let's say that I have 35 grams of each. 35 grams of aluminum, and then let's say 20 grams of oxygen. Yeah. I was thinking of having them be the same, but I think this might be more fun. Let's do it that way. Okay, and so now the question is, what is the theoretical yield of aluminum oxide? That's kind of tough. Now, in order to do this, there's a couple different steps. First off, we have to figure out what the limiting reactant is, right? Because whatever the limiting reactant is, that's going to determine what our theoretical yield is. Okay? And that makes sense, right? If I'm using up aluminum and oxygen, and let's say that I have more aluminum, right? Even though I have more aluminum than I have oxygen, right? Just because I have more leftover aluminum doesn't mean that I can keep producing stuff after the oxygen is gone. The limiting reactant signifies the end of the reaction, right? So when I'm trying to figure out what the theoretical yield is, I have to use as my moles, I have to use the moles of the limiting reactant, okay? So we have to, number one, figure out what the limiting reactant is. Once we know what the limiting reactant is, we have to convert from moles of the limiting reactant. Actually, you know what? Let's type this out. This is just turning into a full-blown example. So how to solve for theoretical yield. A guide for the curious. Number 1. Calculate the limiting reactant. use moles of limiting reactant to convert to moles of product. Convert moles of product to grams of product. Okay. Calculate the limiting reactant is embedded in the previous protocol we have up there, right? And then converting from moles of limiting reactant to moles of product is what we did earlier at the top right with respect to stoichiometry. Okay. But that's how we do it. So let's put this together in this actual problem. So first things first, we have to calculate the limiting reactant. In order to calculate out the limiting reactant, remember, our first step we got to do is we got to convert these guys to moles. All right. So there's 20 grams of, I'm going to put O2 over here. I'm going to put aluminum over here as the, yikes, that's a weird looking A. Aluminum right there. I'm sorry, that's just going to bother me. Okay. That's still bothering me, but I'll just ignore it. Okay. What was I saying? Yes. So we got to calculate the limiting reactant. In order to calculate the limiting reactant, what I got to do is I got to divide, I got to figure out how many moles there are of each of these, right? Oxygen has 20 grams and a mass of 32, right? Because there's 2 oxygen atoms in there. So 20 divided by 32 equals, oh, we did this already, is 0.625. That's how many moles of O2 there are. Aluminum, it's we have 35 grams of it. Its mass is 27. Okay, so 35 divided by 27 is 1.3. Okay, that's how many moles of aluminum there are. Next up, we need to figure out which one of these, there's more moles of aluminum, right? But also aluminum's getting used up at a faster rate. So we need to figure out which one's going to run out first. In order to do that, we take our moles of O2 and divide it by its corresponding coefficient. The coefficient here is 3. Okay. So if I do that, 0.625 divided by 3, 0.208. Where's my pen? Here we go. 0.208. Aluminum, on the other hand, has 1.3 moles. And its corresponding coefficient is 4. Okay. So 1.3 divided by 4, 0.325. Okay. So that means then that aluminum can power it 0.325 times and oxygen can power it 0.208 times. So that means that oxygen is our limiting reactant. Okay. So that means that we're going to be using this amount of moles to solve for the theoretical yield. You don't use this number. Inevitably, people will get tripped up on this, but you don't use this number. You're only going to use the moles, okay? So now we need to convert from moles of oxygen to moles of aluminum. So how do we do this? Well, it goes 0.625 of oxygen, and we're going to multiply by the coefficient of what we want to turn it into, which is aluminum oxide. And we're dividing it by the coefficient of where we're coming from, which is oxygen here. Okay. And that'll tell us how many moles of aluminum oxide there are. So that is 0.625 times 2 divided by 3. All right, so this will make us 0.417 moles of aluminum oxide. Okay, we're not quite done yet. We're not quite done yet. because we need to convert from moles into grams. So the way we do that, if you recall, is we have our moles times molar mass. And that means that we have to multiply 0.417 by the molecular mass of aluminum oxide, which is, there's 3 oxygens. So that is 16 plus 16 plus 16. And the aluminum is, what was it? 27. So there's 2 27s. So plus 27 plus 27. So overall, 102 is the mass of aluminum oxide. And that should give us times 0.417. If I multiply these guys together, then I'll end up with 42.5 grams of aluminum oxide. Okay. So that, guys, is our theoretical yield based off of starting components of aluminum and oxygen. That is what I have for you guys today. I know it ran a little bit longer than I guess I predicted, but I wanted to give you guys a more difficult question. Honestly, you can ask similar questions. You can ask something like, all right, how much, if I have this amount of this reactant, how much of this other reactant do I need in order to use that up, right? So how many, if I wanted the moles to be equal at the end, right, how do I ensure that? So there's different ways you can figure that out as well. We'll go through some of these in class. But for now, I'm going to wrap up there. Basically give you guys another another whole lecture, but this is a tough concept, and I know I wanted to walk through it carefully with you guys. But that's all I have for you guys. You guys have an awesome day, and I will see you guys in class.